this is just a reminder, okay? We did this earlier this semester, where we had a parametric curve, and we wanted to calculate the length of the parametric curve as it's winding through 3D space. That was the integral formula for the length of a parametric curve. Does everybody remember that? Okay. So, what we're doing today is similar. If you are asked to calculate a path integral over a path as that path is passing through some scalar field in 3D space, then the way you're going to calculate that path integral is you're going to put your little scalar field in the integrand along with that integrand formula for the length of the curve, because a path is just a parametric curve, right? And so if you do this in the integrand, that is going to be what gives you sort of the sum of all of the little bits of the scalar field that lie along that path. And obviously if the path is longer, then you're going to have a larger integral, assuming that your scalar field is positive. And anyways, make sure you have that formula in your notes. Like I said, there's like 4-ish, maybe 4 or 5 homework problems that will ask you to calculate a path integral, and this will be obviously a question on your exam next week.
Does it also work like for a surface integral, like for a scalar field?
We're going to do that in a few days, probably next week, if not the week after. But that'll happen.
Like the same logic, with the same logic, adding up, supplying a little bit of stuff.
Yeah. Okay. All good? Yeah. Okay. Then another different type of path integral is you might have a path integral over some path that winds through a vector field. And so that kind of path integral, the formula would be to take the dot product, because we want the integrand to be a scalar, so this has to be the dot product. And we're taking the dot product between the vector field, which would be like a 3-dimensional vector if we're talking about 3-dimensional space, and d gamma dt, where gamma is the path, so gamma is a parametric curve, so gamma you can think of as like a vector with 3 entries. So the derivative with respect to t just means you take the derivative with respect to t of each of the 3 entries of the vector, and so that's also a 3-dimensional vector. So we're taking in the integrand a dot product between 2 3-dimensional vectors, and then we'll integrate with respect to the way that we've parametrized the curve. Okay, so let's do some examples. This example says, find the total mass of a wire with the shape given by gamma and the density given by rho. And so this is a path, or this is a parametric curve, right? Through space. Let's see it. And then this rho, it's only a function of z, but this is what I would call a scalar field. You could have a more complicated scalar field, right? You could have a scalar field that depends on the values of x, y, and z. But this particular scalar field is a pretty boring scalar field. It just increases in value as your z coordinate increases. So what we would do if we want to find the total mass of this wire is we would take the integral over gamma of rho ds, but that is going to be the integral from 0 to 4 pi of 1 plus z times the square root of, well, we'll have to take, first of all, I have to figure out what would be the derivative with respect to t of cosine. That would be negative sine. And if I were to square that, then this would be sine squared. And then I would have to take the derivative of sine, which would just be cosine, and then whenever I square it, it would give me cosine squared. And then the derivative of t with respect to t would just be 1, and if I square it, it would just be 1. So what happens inside the square root is we take the derivative with respect to t of those components, and then we square them, we add them together. Right? You have this in your notes, but that's what we're doing right here. And then we'll have sine squared t plus cosine squared t is just 1, plus another 1 is 2. Okay? But my z is going to be given by my path. And so an integral where I have 1 plus z, well, z was just equal to whatever the value of my parameter t was. And then, yeah, you're right, Gabriel, you just take out that constant and call it square root 2 times that. Okay, and then this is hopefully pretty easy, and you guys see how you would evaluate that by taking the antiderivative and plugging in the bounds and so on. But that would give you the total mass of a wire with this kind of shape. This is a helix shape, and a density of like mass per unit length that changes based on where you are on the wire. And I know it's maybe been a few weeks since we saw this, but in GeoGebra I can hopefully graph the curve cosine t, comma sine t, comma t. And if I let t go from 0 to 4 pi, then it's going to be a little helix shape, little spiral, like that. So imagine this is my wire, and the density is increasing as we go up in the blue direction, and that's what we just calculated the mass of. Any questions about that one? Pretty straightforward. Okay. Well, cool. Next example. We've got find the total work. And so remember, work, if you have a constant force applied directly in the same direction of some distance that you're traveling, then work would just be force times distance. But things get a little bit more complicated, as we learned last semester when it comes to work, because the force isn't always applied directly in the direction of movement, and sometimes the force changes, and sometimes, so on. So this is going to be find the total work done by the force field F. So that means F is going to be a vector field of force vectors that are acting on this object, of an object passing through the field along the path gamma. So once again, gamma is the same parametric curve. It's the same helix. So imagine some object traveling along the path of that helix, and it's in this force field where the force is just going to be equal to the coordinates, x, y, and z. So if you are like in the first quadrant, then you're going to be pushed away from the origin in the direction you are away from the origin. And again, we only care about the force that's in the same direction of the movement of the object whenever we talk about calculating work. And so this is a perfect application for a path integral over a vector field. So if I calculate the integral of my force field, d gamma, then this is going to be the integral from 0 to 4 pi of my force vector field dot product with the derivative of gamma with respect to t. So both of those are 3 entry vectors, and then dt. So my f vector is just the vector x, y, z. The d gamma dt vector is going to have the 3 entries negative sine t, cosine t, 1. So their dot product is going to be x times negative sine t plus y cosine t plus z. Oops.
I wish we had this kind of videos, test.
What?
Midterms. I wish we have we had this kind of intervals.
Yeah.
Midterms. You have this kind of.
Yeah, next week. Next week this will be on your.
The same one, that cancels out the zeros. Yeah.
I can't promise you anything. I would just say, if you work the homework problems that I've assigned, then you should be ready for the test. And if you're having trouble with the homework problems, then remember to ask me on Monday, and we'll do the solutions together on Monday. Yeah.
It looks like much more accessible
than it could be. Yeah, I could make them really difficult. Well, if I make it so that the integrand gets too crazy, I could always just say set up the integral but don't evaluate it, So that way I can test you on it and make sure that you know how to turn one of these path integrals over a vector field into just a simple single definite integral with respect to t. There's only t's in the integrand. And then if it's to the point where it's too difficult to actually take the antiderivative, then that could be just where the problem ends. And I could do that on a test. But you're right, these examples work out nicely. Okay, so what should I do? Because I need this integrand to be in terms of only t, right? So how do I get rid of the x and the y and the z?
X is cosine t, sine t is y.
Yeah, exactly. I'm going to go back to the definition of my path to grab the x and the y and the z definitions, where x is cosine of t, y is sine of t, and z is t. So, integral 0 to 4 pi of negative x sine of t, that's negative cosine t sine t, plus y cosine t, so plus sine t cosine t, plus z, which is plus t, dt. I'm sure this is what you're referring to, but now I just have the integral from 0 to 4 pi of t dt, which I'm sure you could figure out.
Who came up with the idea of curl? That's interesting. Who thought about it first?
I mean, that is a good question. I'm sure Wikipedia has the answer. Okay. see how far we can get in this example in the next 8 minutes. But find the total work done by the force field F on an object passing through the field along the path gamma. So we've got the same path gamma as before, but this time our vector field that we're passing through has a little bit more complicated formula. And this is, let me rewrite it in a different way. But what this is it's negative x over x squared plus y squared plus z squared to the power 3/2, which would be like taking the square root and then raising it to the third power, right? But I could just write it to the power 3/2. And then I would have the same expression for my second entry, except I would just replace the negative x with the negative y. And then for the third entry, I would just replace the negative x with a negative z. And that is my vector field F. So for this, what do you call it? For this integral we're trying to do, the integral of f d gamma, this is going to be the integral from 0 to 4 pi of this vector field F dot product with the derivative of gamma with respect to t dt. So if this is F, and I'm trying to take the dot product between F and the derivative of gamma with respect to t, the derivative of gamma with respect to t is this vector. This dot product is going to be really big and nasty. So, hope I left enough room here. It's going to be negative sine t times x. Actually, maybe before we move on, we should do a little simplification. So, what is x squared plus y squared plus z squared? That would be cosine squared plus sine squared plus t squared, right? So cosine squared plus sine squared is 1, and then z is t, so this is 1 plus t squared. So at least I can replace that with 1 plus t squared to the 3/2 power. And then now whenever I take this dot product, I'm multiplying everything with the same denominator, so whenever I do the sum, they're all going to have the same denominator. So in the bottom here, I can just write 1 plus t squared. Okay, now up top, I have to worry about what is negative x times negative sine t. Well, it's negative cosine t times negative sine t. That's cosine t plus sine t. No, cosine t times sine t. Okay, and then for my second entry, I'll have negative y times cosine t, which is negative sine t times cosine t, so that's minus sine t cosine t, so that'll cancel. And then for my third entry, I have negative z, which is going to be negative t, times 1, so it'll be minus t. Yes, it should. Thank you. Okay. So obviously, yeah, part of that cancels. And I have the integral from 0 to 4 pi of negative t times 1 plus t squared to the power 3/2 dt. Of course, we could take out the negative sign because it's a constant. But what should I do here to solve this integral? A u sub, where u is 1 plus t squared. And so that means du is equal to 2t dt. So yeah, where I have t dt, I can just make it du over 2 and make this negative half integral of u to the 3/2 power. Yes. Yeah, definitely. Very lucky that you guys are paying attention and catching my mistakes. Okay, so if I plug in 0, then 1 plus 0 squared is 1. If I plug in 4 pi, then I get 1 plus 16 pi squared. So the balance kind of got nasty. But you can see where to go with this. This is clearly just a antiderivative power rule, and you could plug in and you could eventually get your answer. Yeah, so what I had planned next, and what we'll try to talk about Monday, is that this vector field is a conservative vector field, and this conservative vector field exactly describes the gravitational field. And it also kinda, we'll talk about it more, but it kinda describes the electric force field if you have opposite charged particles, but the electric field is more complicated in some ways. And so I like limiting the discussion to just the gravitational field. This field, I want to say that this field where it's just x, y, and z, I think that's also conservative. There's only one way to test. We could do the curl, right? So if my field is x, y, z, and all I have to do to figure out if it's conservative or not is take the curl. And so the curl tells me to do the cross product between the nabla operator and my field, which is x, y, z. Then this is going to be I times the partial derivative of y of z, which is 0, minus the partial of z of y, which is 0, minus j times the partial with respect to x of z, minus the partial with respect to z of x, plus k times the partial of x with respect to y, which is 0, minus the partial of y with respect to x is 0. So the curl is the 0 vector, so this is a conservative field as well. Be a little bit trickier maybe to prove that that is a conservative field, but it is.